Hello, everyone. Thank you so much for joining our lesson again. In my previous lesson or my previous presentation, I explained how we calculate work done, and also I explained our theta in as far as work done is concerned. And I also showed you the right formula for calculating work done, and we were only focusing on work done by force applied, and I used that to explain how we determine our theta for work done. Now, on this lesson or presentation, I wish to extend my presentation to other forces other than work done by force applied only. So I'm going to have a different diagram, slightly different, because I'm going to set friction on this one. Right. Suppose I've got a surface here, and on this surface, I've got my object, or I've got my block. We worry less about mass for now. Let's say this block is being pulled to the right by a force of 150 newtons. And remember, I said this force must be a constant force. And it is pulled for a distance of, let's say, 8 meters, right? And as it is being pulled to the right, it experiences a constant frictional force, right, of 4 newtons. And we all know that friction opposes motion, right? So if the object is going to the right, friction is going to the left. And you know, on definition and the characteristics of frictional force, number one, it is a force that opposes motion. And number two, it is a force that acts parallel, right, to the surface, right? So the direction of friction is not going to be a problem there. Now, the first question, it says, which is item A, and I want to believe that this is my example 3, all right? The one that I'm doing now, it's fine. I'm going to use it just to explain some few concepts here, right? What is happening here on the, so this is my example 3, right? I don't want us to lose it there. So this is my example 3. So A, it says draw a free body diagram, right? And this free body diagram must show all the forces acting on the block as it is moving through that distance of 8 meters, right? Then item number B, it says calculate, right, work done by applied force, right? Fine. Item number C, I'm going to expand it like I promised. Calculate work done by frictional force. Right. Calculate work done by frictional force. And then item number D, calculate work done by normal force and gravitational force. So I've decided to combine D, that is normal force and gravitational force, for the sake of time and space. So that is what we have at the moment. So you can all see there where we presented, it's a block on a surface, and we normally represent our surface with those lines to show that that is the surface. And this block is going to move a displacement of 8 meters, being pulled by a constant force applied of 150 newtons, and it is experiencing a constant kinetic friction of 4 newtons, right? And this is our example number 3. Now, the first question A, so we have our solutions here. I don't know if it's going to fit all the calculations on one page. Let's go to A. Can I divide this into two so that at least all my answers can fit here? So I'm going to do A, B here, then CD on the other side. Correct. So A, it's a free body diagram. As usual, I put my dot to represent the object, and then we identify the forces acting on the block. So I've got my force applied, which is going to the right, and that is force applied. And then I've got my Fg, which is going down, and then I've got my Fn, which is going up and perpendicular to the surface. Now I've got a new force that has been introduced, which is frictional force. So if the object is going to the right, I want to believe that we all understand the direction of friction because it always opposes motion. So the object is going to the right, so friction must be going to the left. So this is going to be my Fk of, or F fric, right? So that is the free body diagram. So obviously that should be carrying 4 marks: 1 mark for force applied, 1 mark for friction, 1 mark for Fg, 1 mark for Fn. Now I want to emphasize some points here. Number one, your normal force is always perpendicular to the surface, not to the ground. Uh, we are going to look at an incline situation next time. Now you realize that your normal force is still supposed to be perpendicular to that surface of the incline. Is that okay? And then Fk is always parallel and opposes motion. That is very critical, right? So that is our free body diagram. We get our 4 marks there. Item number B, what are we calculating? Calculate work done by applied force. So the formula for work done, you bring it on. It says work done by force applied is equals to force applied by displacement by cos theta. That's fine. So I make proper substitution. Work done by force applied is because what is the magnitude of force applied? It's 150 newtons times displacement, which is 8 meters times cos. Our theta there. Remember, I want to emphasize this. Our theta is the angle between force and direction of motion. So my theta is 0 degrees, which gives me 1 as well. So my work done by force applied is going to be, you take your calculator, uh, you punch cos 0. By now you should be knowing this, eh? It always gives you 1, right? So in other words, your calculation is just supposed to be 150 times 8. It's only 150 times 8. It's 150 times 8. 150 times 8, it gives me 1,200 joules. Right. Good. So that's our answer. You underline it. Now let me preempt something on that one. We are getting a positive work done. It means uh, force applied is doing positive work on the block. Right? And remember, in my introduction, I said work done is equals to energy transferred. So what it means is the object, the block which is being pulled, has gained 1,200 joules. That's the interpretation of the answer there. So whether I say calculate work done by force applied or calculate energy transferred to the object, we still get 1,200 joules. So the object here, because this is positive work, so the object has gained 1,200 joules, right? But if we get a negative answer, like what we are going to get for friction, I think that's our next item, which is item number C. When we get a negative work done, it means the object has lost energy, right? So item number C, quickly, it says calculate work done by frictional force. So work done by Fk is equals to Fk by displacement by cos theta, right? So our substitution follows. The magnitude of the frictional force is 4, right? times our displacement, which is 8 times cos. Now, where is the object going? The object is going in which direction? To the right, and it's horizontal. And then friction opposes. So the angle between force and direction of motion is obviously 180 degrees. So let's take note of this. Whenever we calculate work done by friction, our theta is 180 degrees. And when you punch your calculator, cos 180 gives you -1. We must know those angles. Cos 180 gives you -1. So obviously you can predict that we are going to get a negative answer there, because cos 180 is -1. So that -1 is going to affect your displacement and your friction. So we are definitely bound to get a negative answer. So work done by Fk is going to be minus, right? So it's cos 180 times 8 times 4. That gives you 32. So uh, we are going to get minus 32 joules. Right. So you underline your answer there. Now, let's interpret this answer as well, friends. We are getting a negative work done here. So what it means is the object has lost energy. Remember, we said work done is equals to energy transferred. So how is the energy being transferred here? Since we are getting a negative answer, it means the object has lost 32 joules, right? Remember, with our force applied, the object gained 1,200 joules, but friction is in the opposite direction. So it's taking away, right? So it has reduced the energy gained by 32 joules. So that's why we get a negative answer, because it's going in the opposite direction and the object is losing energy, right? So whenever we calculate work done by friction, we must always get a negative answer. Whenever you get a positive answer for work done by friction, it means you must visit your theta. It means your theta is not correct. Right. Then finally, let's look at item number D, and we just quickly summarize that. I'm not going to waste much time there. Calculate work done by normal force and gravitational force. So let's start with normal force quickly. Work done by Fn is equals to Fn by displacement by cos theta. Right. Um, I am not even going to waste your time by calculating my Fn. Yeah, if you want, I can do it quickly, but for FG, I'm not going to waste time there because it's the same concept, right? So work done by Fn is equals, how do we calculate Fn? In this scenario, your Fn is equals to Fg, right? So which is also equals to mg. So this is going to be mg represent Fn times our displacement, which is 8 times cos. Now, I'm not even going to worry about mass because our theta is going to solve all our problems. Now, look at Fn. Fn is going up. It's perpendicular to the surface. So the object is going to the right, Fn is going up. So your theta there is going to be 90 degrees. So you quickly go to your calculator. Cos 90 gives you 0, right? Cos 90 gives you 0. So it doesn't matter the mass of the object, it doesn't matter the displacement. The moment the force is perpendicular, your theta is 90 and cos 90 gives you 0. So this 0 nullifies everything. So I can make my conclusion to say work done by Fn is equals to 0 joules. The same applies with work done by Fg. In this case, in this case, your FG is also perpendicular because this is a horizontal surface. So work done also by FG, I'm simply going to write the answer is 0 joules. Reason they are perpendicular, right? The forces, I hope it's clear there. Yes, the forces are perpendicular, right? Perpendicular to the surface. The forces are perpendicular. Right. So this is it. I've introduced work done by friction, and we have now concluded on the perpendicular forces. that in future we don't waste our time calculating work done by perpendicular force, because your theta there is your theta is 90, and cos 90 gives you it gives you a 0. So in our next lesson or our next video, I am going to introduce two things. Number one, I'm going to introduce an incline. Right, how do we calculate work done on an object when there is an incline, that is a surface that is elevated from the ground? So after that, I'm going to introduce you to how do we calculate net work done, and then we take it from there. Thank you for joining us in our class, in our presentation, and must take care. Thank you. Love you all.